Juven? Can you hear me?
Yes.
Oh,
Hi, welcome.
hey.
Let me make
Where's
啊，
where is this?
伟大的先行者
喂，这是中山陵吗？
啊，
哦，我都不记，我可能就去过，我有没有去过我都不记得了。
天下为公，世界道。
嗯，还是
两岸
蓝字
两岸人民共同尊敬的是先行者，
哦。
因为他是广东人嘛，你不是广东人吗？
我是广东人，对的，对，对，I see 这个 interesting。
你会讲好谁嘞？
猴猴塞雷，好的。
今天 Ryan introduce 你，所以我没有办法讲 Cantonese。
哦，没有，你可以，你可以在最后讲 if you wish。嗯，
多谢大家，多谢大家要怎么讲？
多谢大家，
多谢大家，
多谢，
多谢大家。
哎，你那个图真的是很蓝的那个顶，这可能是调过的，怎么这么蓝？要不我试一下 share 那个 screen，看看能不能 work。
我更绿，你可以给我看。
Yeah, okay. I have permission. Oh, this will stop other screen sharing. Oh, 你在 share screen, I see. 我能 temporarily. Okay, let me just try. Everything okay? 我调一下这个东西。Is that all right? Hi, Juven. Is that looking okay on your side?
Chao-Ming，
嘿嘿嘿，
你可以寄你的那个这个给我吗？有口音。
你说是你这个
这个投影片。
哦，这个 slides, yeah, yeah, of course. I'll do that afterwards.
杜培今天是 Ryan 对吧 ？Ryan host， 我记得。对，我们I'm waiting for Ryan.
Okay, yeah.
He should be the host today. But I can do it if he didn't show up. I mean,
Okay.
he doesn't show up. Let's see. Okay. Maybe we should just start. I think. Let me not wait him.
Mm-hmm.
Okay, Ryan is not here, so let's start. Let's see. Welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics Seminar Series. 欢迎大家来到哈佛大学的 量子物质 seminar. Today we are very honored to have Professor Chao-Ming Jian, Chao-Ming from Cornell University. Chao-Ming studied his PhD at Stanford University. Then he went to KITP and also Station Q for his postdoc. Currently, he is an assistant professor studying his professorship at Cornell University. It is our great honor to having him today to tell us a story about entanglement criticality in random Gaussian circuits. And that's only welcome, Chao-Ming. Please take over.
Okay. Yeah, thank you, Juven, for the nice introduction. Yeah, so today I hope to tell you a story about entanglement criticality. So it's what I think is a very interesting and new type of criticality that people have been actively exploring these days. And I will go rather slow in the intro part. Hopefully, for the experts, you won't get too bored with that. Okay. So before I begin the actual content, let me thank my collaborators on related projects, Professor Yizhuang You from UCSD, Professor Romain Vasseur from UMass, Professor Ludwig from UCSB, and Anna Kesselman, who's at KITP, and Bella Bauer from Station Q. So this talk will mostly based on the second work, and then I will also mention some interesting aspect provided from the first work as well. Okay, yeah, so let's get started. I guess nowadays when we talk about quantum phases of matter, try to classify them, I guess these principles always come immediately to mind. For example, we classify phases of matter by their symmetry property, and nowadays we pay more and more attention on the topological properties as well. And then so these two sort of forms the pillars, these principles forms the pillars of current day classification of phases of matter. Yes, yeah, and then if there's any change to the symmetry property, whether or not you break it or spontaneously or not, or whether or not you have you can go from some state with one type of topology to a state with a different type of topology, any such change would trigger quantum criticality. Right, so this is sort of the one quick big picture type of review when it comes to classifying quantum phases and criticalities at equilibrium. Okay, but nowadays besides symmetry and topology, people start to pay more and more attentions to quantum entanglements in condensed matter. In particular, we start to realize that many interesting many-body phenomena cannot exist without having interesting entanglement structures behind it, right? But quantum entanglement is rather a unique property of quantum mechanics. Usually, if you want to characterize how much entanglement there is, a frequently used or one of the most widely used measure of how much entanglement there is lurking in the background is this quantity that is called entanglement entropy. So supposedly you have some reduced density matrix rho on a subregion A, then you can just use this formula to calculate the entanglement entropy of a region A, and basically this is a characterization of how much entanglement there is between the degrees of freedom inside A and degrees of freedom outside of A. Of course, I'm assuming that the global system is in a pure state. For example, it could be in the ground state. Right? Okay. Yeah. So this is certainly an interesting quantity to explore, but you can see that there's a log of density matrix showing up. So that makes it slightly more difficult when it comes to trying to calculate what that is in different phases of matter, and it certainly make it even harder for us to measure such a quantity, the entanglement entropy, in experiment. Well, yeah, but we just did not. Well, condensed matter is always advancing, so I'm really glad to see that there's this very nice work showing up on Nature 2015 that people start to measure entanglement in experiment. Right? This is done on an atomic microscope in Marcus Greiner's lab at Harvard. So they actually successfully measured entanglement, albeit for a very relatively small system, but I think this is a very important advancement in trying to in our attempts to trying to understand quantum entanglements in condensed matter physics. All right, and then also, these days people are actively trying to explore quantum entanglement also for the purpose of quantum computation, cryptography, and etc. All kinds of applications that try to make use of the quantumness, in condensed matter or related systems. Right. Okay. So I was talking about quantum entanglement and quantum entanglement entropy, right? But if I want to, since this is a really important notion, I could always ask this rather fundamental question. I think is that could this be a third element besides symmetry and topology that allows us to define interesting phases of matter, right? So are there phases of matter that is completely defined by their entanglement property and possibly nothing else, right? Well, this is really a big question, but we certainly have already collected a lot of information about this, in the previous studies. For example, if we focus on Hamiltonian systems, then we know that ground states of a local Hamiltonian system most likely follow the area law entanglement entropy, meaning that the entanglement entropy of the ground state, a single pure state, the ground state, actually is going to scale with the size of the boundary of A. All right, that's called the so-called the area law, right? Because we're assuming, I guess, when this name was invented, we were assuming that everything is sitting in 3 dimensions. So the boundary of region A is called the area law. And well, with Fermi liquid as an exception, but one can argue if Fermi liquid can be truly stable at 0 temperature. So, but most likely when we talk about a ground state of a Hamiltonian system, we can encounter area law entanglement entropy, right? However, if we switch to some highly excited state, an eigenstate that with a relatively high energy or energy density, then we have this very interesting hypothesis, the so-called Eigenstate thermalization hypothesis, ETH, put forward by Schrednicki and Deutsch in these papers. It basically says that every single highly excited eigenstates is supposed to follow this volume law, meaning that if you just measure the entanglement entropy in a subregion A, it's going to scale with the volume of the region A you're interested in. Obviously, this is a hypothesis. It seems really general, as in it doesn't really care about the details of the Hamiltonian, right? But so far, it's still called hypothesis because it's unproven, and in fact, people have already realized that there can be counterexamples to this, which is another very interesting notion, which is called the many-body localization. In such systems, in fact, if you just solve for, if you just diagonalize the entire Hamiltonian, you realize that most of the eigenstates would have area law entanglement entropy. So obviously, this would be an exception. The MBL, many-body localized phases, would be an exception to ETH, right? So you may want to think these represent different types of phases of matter. Okay. However, now we're not only talking about a ground states or something that happens at a certain temperature. We're talking about properties of the whole spectrum, right? So maybe we're stepping already outside of the domain of phases of matter at equilibrium and getting into the domain of phases of matter at non-equilibrium, right? With that in mind, we could try to view this from a slightly different angle, as in, if I don't want to solve the complete Hamiltonian, right? Maybe I can think about a different process to define, to sort of make a difference between the two, right? For example, we can think about their dynamics. Since when we talk about dynamics, that starting from, say, doing a quench experiment, starting from a product state, this whole evolution process would be able to access not only the ground state, but also highly excited state, the behavior of highly excited state as well, right? So for example, when we start with a 1D chain with a product state, with a product state, which is a pure state, and we can turn on the Hamiltonian and watch how the system evolve and try to keep track of how the entanglement entropy in particular evolve for a subregion A. right? So it's, this is certainly not the definition of ETH, but it seems also rather universally happening in ETH system. If you have a thermalizing Hamiltonian, then as you let the system evolve, the entanglement entropy would grow linearly, right? So it's a relatively fast growth of the entanglement until it's saturated to a volume law value, all right? So that's what's happening for ETH. However, if you switch to MBL systems, or systems in the MBL phase, and if you do the same quench experiment starting from a product state, you realize that the growth of entanglement entropy is rather slow. It follows a log, right? It eventually still grows to big values, but I would say that for a long time it got stuck in relatively low entanglement entropy states, right? Maybe I could say that for a long time this is sitting at somewhat some state that is somewhat close to an area law situation, right? So so certainly I could, from this perspective, maybe we could try to distinguish ETH and MBL just from the perspective of entanglement, right? So now if we talk about the phase transition between ETH systems and MBL systems, maybe this could be viewed as an entanglement criticality. But I put a question mark here for multiple reasons, because I think it's fair to say that ETH and MBL transition is not fully understood, to every little details, its universality class and the exact formulation of it. Many things are still, to be are still under active investigation. And then also you may want to argue that the entanglement feature may be just piggybacking on what the real physics is, whatever the real physics might be. So whether or not entanglement is really playing a central role in such a system, I think it's possibly an issue of perspective, or maybe we need a deeper understanding of this transition to understand if it's more properly viewed as if it should be more properly viewed as an entanglement criticality or not. Okay. So, and also, this is certainly we're talking about ETH versus MBL, meaning that we're talking about Hamiltonian systems, right? But it could be that maybe having energy conservation in a Hamiltonian system is making things more complicated for us to analyze if we really want to just target at something that is showing entanglement criticality in a pure form, maybe, right? So for the rest of the talk, I won't be talking about ETH versus MBL, but rather I would like to switch to a different setup where we can define things, more cleanly. And I hope the system that I'm going to introduce to you is going to be more unarguably a showing at different entanglement phases and entanglement criticality. Okay.
I have a question, if I could, quickly.
Yes, please.
Is there any dimension dependence in this logarithmic result and this slow growth?
Oh yeah, here I'm talking about one dimension for specifically.
So what happens in higher dimensions?
Higher dimensions. Well, okay, there's already a debate whether or not MBL exists in higher dimensions.
Sure. Okay.
So
yeah, I just wondered if there was a predicted exponent, a sublinear exponent.
Yeah, I guess I shouldn't comment on that too much.
Okay.
Yeah,
thanks
sorry.
anyway.
Yeah. Right. Okay. Because also, I also sort of skip over a so-called pre-thermal regime. So there could be a lot of extra subtleties in this type of story here. Okay. So now I'm going to move on to a different setup that is certainly inspired by what I explained in the last slide, as in maybe we could just think about entanglement phases as some phases that exist in dynamical systems. The dynamics could be generated by Hamiltonians, or it could be generated by Hamiltonians plus other factors, which I will tell you about what these other factors might be. But I guess the spirit is similar. We could just think of generally a system of qubits or spins or whatever degrees of freedom you're interested in. I'm just drawing a 1D chain here, for example. That's my system of qubits. And then it could go through a certain type of quantum evolution, indicated by this. Maybe I should color it black, but this blue block. There's a green a box, right? So right now we haven't looked at what's happening inside, but so long as we have a dynamical system, we should know how a quantum state evolved. We could do the same thought experiment as in we could start with a product state, which is a pure state, and it has very low entanglement entropy at time 0, and watch how things evolve at a later time, right? In particular, I could focus on a certain late time and focus on a subsystem A and just ask what kind of entanglement entropy I would get, after some time, after the evolution of the system for some time. Right. In particular, I'm interested in the late time behavior, the saturated behavior of the entanglement entropy at, say t equal to infinity. Obviously, things that proper thermodynamical limit has to be taken, which I will get to shortly. But we could ask, we could at the very least make a formal definition for the moment that if the final saturation value of the entanglement entropy follows a volume law, then we call this volume law phase, right? And then if the final saturated value stays low as an area law, SA proportional at final time is going to always proportional to the size of the boundary of the region, then we call this an area law phase. And these phases are really phases for the dynamical system. It tells you about the intrinsic property of these dynamical evolution. All right, given by this box so far, right? But you could say that now I'm just putting out some formal definition, and is it realizable? Are there really systems that can exhibit these two phases? Well, indeed, there is. It was first put forward by.
Excuse me.
Yes.
Sorry, to make sure, when you say entanglement criticality, what parameters are you tuning now?
Yeah, I will get to that.
Okay.
Like now, okay.
And then
so
the thing you have in mind is a continuous transition.
It could, well, yes, like I will show you examples where it's just continuous transition, second order or possibly higher. But I'm not saying that first order transition could never happen.
Okay.
Yeah, I guess it's a general rule of thumb that maybe first order transition can always happen, and second order transition has more structure to it, maybe. Right. So I was explaining things in rather general context, but you may always wonder if those things are actually realizable or just a pure theoretical construct. But it was, really these two seminal work that triggers a real surge on, I think, a real surge on in this direction. So it was these two works that propose an actual setup that not only exhibit the two kind of phases that I was talking about, and also there is a very interesting criticality separating the two phases. All right. So let me give you a brief overview of what happened, what's introduced in these seminal works. Right, so now I'm going to not talk about a Hamiltonian system. There's no Hamiltonian in the system, but the dynamics on this on the qubit system. Now I'm focusing on qubit chain, just one dimension for now. Qubit chain, and then as it evolves, we just have to design the quantum evolution in this setup, right? So the horizontal direction is space, vertical direction is time. And then the spatial direction is where the one-dimensional chain lies, right? So the evolution of the quantum system are governed by this circuit. Each of the green block will let the qubit nearest neighbor qubit interact, and they are just completely independent, two-site random unitary gates or Clifford gates. Right. Clifford gates is whatever the preserve. It's the operation, unitary operation that preserves the Clifford group. Okay, that preserves the Pauli strings. All right. So this certainly makes things scramble. using this term, as in it just try to create entanglement from a product state. Also, I have this this red box. Each one of these is a one-side projective measurement. All right, and you see that they're somewhat randomly distributed across the circuit because there is a parameter here, which is P, which means that every spin is measured with probability P. It's a classical probability in every time step, right? So sometimes the system, the spin may not be measured, sometimes it's measured. When it's measured, it's represented by this red little box here. Right? Okay, so this will be our tuning parameter to answer Juven's question. But let me explain a little bit more about this one-side projective measurement. Right, so this is not something that is usually encountered certainly not encountered in a Hamiltonian system, and this is the type of measurement that really induced the collapse of quantum states. You know, it's the type of measurement that we learn about when we start learning about quantum mechanics. In particular, follows the Born rule, meaning that if a many-body state coming in, the measured spin will collapse after the one-side measurement. All right. I have no way to control the outcome of the collapse unless this measured spin is already pointing along one of the basis direction. But in general, I will just get two possibilities, either up or down, assuming I'm measuring it along the z basis, and the probability of each outcome occurring depending on the incoming state, right? So I could possibly have these two outcomes, right? But if you don't look at the outcome, you would say that maybe I'm just gonna get a mixed state. If you keep track of the measurement outcome, then you know which state the system collapsed to. You know, so the idea is that if you have a state incoming, and then one of the spin is measured, and you keep track of the measurement outcome, then for each measurement outcome, there is a pure state coming out of it, and the measured spin become disentangled with the other spins in the system. All right. So this is certainly not something that we would encounter in a Hamiltonian system, and it actually is a very interesting new ingredient to a dynamical system that actually triggers the existence of an interesting phase diagram. All right. So now combining these random unitary random Clifford gates, you know, these green blocks, and then these one-side projective measurements, we have our dynamical system. All right, here I emphasize that even though I have lots of measurements in the system, but if you keep track of the measurement outcomes for every single measurement, then there is a pure state at the final time slice. If you wish to terminate the circuit at time t, there's always a pure state at any time corresponding to a given set of measurement outcome. But the pure state may be different. Well, will probably most likely be different for different measurement outcomes. All right, so I end up having a collection of states, or rather an ensemble of states at the final time slice. All right, and these papers study this setup, looking at what can happen at the final time slice, this collection of states. Right, so what they study is the averaged entropy, average entanglement entropy in a subregion for this final state, right? And then there's this very amazing phase diagram, you know, with P as the tuning parameter. Remember, P is the probability each spin is measured at every single time step, right? So for P close to zero or zero, the circuit is mostly consists of unitary gates, meaning that, well, so that means if you start with a product state, entanglement entropy will grow rather quickly, most likely linearly, ballistically, and then quickly saturate to a volume law at a finite, after a certain time, after a certain thermalization time, if it will. And then, so this is where the volume law phase lies, because a long time, the entanglement entropy scales as the volume. All right. And then if you have a high probability for measurement to occur, then, you know, for example, you could think about the limit where P is 1, then every single time step, all the spins are measured. Then when every single spin is measured, the system becomes completely decoupled and collapse back to a product state, right? The product state may be different for different measurement outcomes, but it's always a product state. So in this end, no matter how long you evolve, the system is going to stay at a rather low entanglement state. And in fact, it's going to be the volume law, sorry, the area law for this part of the phase diagram. If you look at the long time behavior of the entanglement entropy. All right. So this is a 1D system. You know, the area law refers to the size of the boundary of the entangling region A. A would be an interval, so the boundary of A is going to be 2 points. So that's why, you know, in this 1D setup, you know, order 1 means area law. All right. And then,
question I could.
Yes, please.
So what is known about the prefactor of the volume law as you approach criticality? And a similar question, what's known about the prefactor of the boundary law? Because you're suggesting that it's just 1 or 2 boundaries. Why not more than 1 or 2 boundaries? So the same question of prefactor in both cases.
Sorry, what does P boundary mean? P factor?
So, so prefactor. So you've got a scaling law proportional to volume, and yes, the prefactor is the scalar which multiplies. So what is known about the prefactor as you approach criticality?
It's certainly explore, but I guess there are some scaling analysis which I cannot remember off the top of my head, but it's certainly decay. It's certainly close to 0 for sure.
It was whether there was a theoretical prediction for its behavior or an empirical observation.
There are lots of numerics on this.
Mm-hmm.
And then I could provide some theory comment on this, but you know, this criticality has not been like fully, completely understood. There's some solvable limit that I can maybe comment on.
Thank you.
Sentences. Yeah, right. So you see that not only there's a volume law phase and an area law phase, but we see that there's what's most likely, and now we understand it has to be a second order, or at the very least a continuous transition between the two phases. And then at the critical point, the entanglement entropy scales as log of the system size. The entangling, sorry, not the total system size, but the log of the entangling area. All right, in entanglement region A. Right, so at the critical value of P, it's between P right at the critical value. Right, so I guess if you're familiar with this, Hamiltonian system that is gapless and in 1 dimension, you would maybe try to compare this situation with the ground state of a gapless spin chain, for example, or the ground state of a general conformal field theory, where a log of entanglement show up. Indeed, that is the case for general CFT, the ground state of a CFT in 1+1 dimension. However, this comparison may be a little bit loose in the sense that here we have no Hamiltonian whatsoever, so there's no ground state to speak of, yet we still see a log behavior. Okay. So this is a rather interesting setup, and this discovery put forward by these seminal works really triggers a surge in the study of quantum circuit type system, in particular their dynamics and possible different entanglement phases. Here I cannot possibly list all of the reference here, but let me just mention quickly that there are lots of perspective people can take on various parts of the phase diagram. For example, there is a perspective provided by this paper saying that the volume law phase is not that trivial, even though you may think the volume law phase is just looking like a thermal bath, but it actually has some interesting quantum error correction property. And then you could also view this same transition I show on the previous phase diagram as a form of purification transition. So this is a sort of a reinterpretation of the previous setup, and then there are much more numerics done on that critical point, trying to extract all the critical exponents there. Right. Okay, and then so in terms of trying to understand this, trying to come up with some analytical understanding of what that transition is. what that transition is. There's these two works, one of them by myself and the other by Choi, Bao, and Altman, that try to come up with a theoretical analysis of what the critical point is in this type of model, where each of the block is random unitary. And then there's a nice StatMag model that comes out of analyzing this, that gives us an idea of what that critical point is, what the phases is, and what the critical point is, and why do we have area law, log, and volume law in the previous phase diagram. All right, it actually has something to do with the symmetry broken phase and the symmetry preserving phase of replica symmetries. All right, and then the critical point is supposedly described by a two-dimensional conformal field theory, but a non-unitary one, a non-unitary conformal field theory. All right, these are more directly related to the setup introduced in the seminal papers, two seminal papers, and there are lots of generalization to other contexts, adding more ingredients to make this more interesting in different ways. So sorry if your work is not mentioned here. There are really a lot of development along this direction. All right. But I think I won't go into the details of these analytic understanding or these other perspectives, but rather I would like to, try to explain to you what I think, what the problem really is. All right. So certainly we could just be faithful with the setup or whatever generalized setup we are interested in. But I think overall there is a structure behind it, right? So I want to say that all these type of problems falls into the categories of a problem of random ensemble of non-unitary circuits. So two things I hope you that can pay attention to is that it's a random ensemble, first of all, and then also it's about non-unitary circuits. All right. I think it's relatively easy to appreciate that we're dealing with a random ensemble because we have a lot of randomness in the problem. For example, each of the gate is a random unitary or Clifford gate, right? And at every single time step, there is a probability that measurement happens. So there's some random distribution of measurements in the space-time. For example, represented by such a picture. These red boxes occurs at random at every single space-time point. And also there is a randomness that comes out of measurements. For example, when we talk about the Born rule for every single measurement, right? We're measuring a qubit. I have no way to control which measurement outcome I would get, right? I could get up, I could get down. When I see up, it means that the state is acted upon by a projector, basically, a projector to the up state on that spin. If we measure the down spin on that site, the system is gonna be hit by the projection to the down spin, right, on that same site, right? There's no way I can control which measurement outcome I get, but I know one of these situations would occur. So this also goes into the randomness of the ensemble, right? So combining all these, for every single realization of the unitaries, every realization of the distribution of measurement, and every set of measurement outcomes, I would have a non-unitary circuit, right? Consists out of projectors on these red boxes and unitaries on these green boxes. Okay, so it's really a random ensemble of non-unitary circuit. So I think this is a helpful perspective, as in it encapsulates. I think it's a general language people can make use of. Not only for this setup alone, but just for also it would include all the later generalizations of random circuit dynamics. Right? And certainly there are non-unitarity in such circuit. Really, in this example, it's coming out of measurements. But another point that I would like to mention is that this is a specific setup that I was introducing, put forward by the earlier works. But in principle, there's no real there's no real need to distinguish which part of the circuit is unitary, which part is not. I could certainly combine a measurement with a unitary rotation, and then that would in general be formulated as some non-unitary process, right? And obviously, and also later we would encounter possibly more generalized measurement that does not completely collapse the state. So in those cases, all of those cases would fall under this umbrella of random ensemble of non-unitary circuits. This language help us to not distinguish so much which part specifically the system is unitary, which part is not, right? But this help us to and obviously this is trying to make use of the concept of universality, as in maybe the details of where exactly the measurement occurs does not matter. We are talking about things that are universal, so they're supposed to be universality classes of circuits or universality classes of dynamical systems with non-unitarities in it, right? But certainly, if I just talk about a non-unitary ensemble, an ensemble of non-unitary circuit, it seems rather general. Indeed, yeah, if you have a circuit whose non-unitarity solely come from measurement, then this ensemble of non-unitary circuit has to satisfy a certain rule, which is that which is basically given by this identity. If you have all the circuit realizations sum up, calculating this C dagger C being one realization of circuit, you have to get the identity operator. This satisfy would mean that C forms a so-called positive operator value measure, POVM. And then, I forgot to cite, but there's a theorem called the Nymark Theorem telling us that as so long as you have this condition, you can realize your system by via measurement and other possible unitary operation, if you wish. Right. And also when it comes to a problem triggered by measurement, then applying the Born rule is certainly a natural choice. And then whatever final average behavior you want to observe in your system, the most natural thing to do is to weigh them by the Born rule. Right. That means each circuit does not necessarily appear with the same probability, because each circuit is corresponding to a certain set of measurement outcomes, and different measurement outcomes can come with different probabilities. That's what the Born rule is saying, right? So these are two subtleties when it comes to non-unitary circuit ensembles coming out of measurement, with its unitarity solely coming from measurement, right? Because you can certainly go beyond that, as in really people are still trying to understand how much, what importance would, how would these change the phase diagram or change the criticality at the critical entanglement criticality at a critical point? Just as a proof of concept, there's this earlier work that basically studied tensor network, which you could reinterpret as a random ensemble of circuits, non-unitary circuit. Presumably there's no POVM condition satisfying here, and then every single circuit is weighted with the same probability, so no Born's rule applied. And then, but even in such a circuit, there's a nice entanglement criticality ensemble of circuit. There's a nice entanglement transition or entanglement criticalities that has been studied. And then there's even speculation that this entanglement criticality is very closely related to the one occurring in the setup I introduced earlier with random unitaries plus projective measurements. But yeah, still there has been a debate about whether or not these conditions really change the criticality, or the entanglement criticality you see in the random ensembles with non-unitarity induced by measurement is fundamentally distinct. Will be fundamentally different if you keep up these either of these conditions or both. Okay. Right. So I guess I will. So this is a rather general overview, and then I would like to pause here for questions before I get into the details of my work on random Gaussian circuits.
I do have. So let me just make sure.
Yeah.
From outsider, So this is a measurement-induced criticality in the sense of measurement.
Yeah, so the initial setup was measurement-induced. This one is not. This one is, you could, well, it's formulated in tensor network, but you could understand it as just a random ensemble of non-unitary circuits with non-unitarity not coming necessarily from measurements. For example, if you run a Hamiltonian that is non-Hermitian, then you may want to say that you have a non-unitary evolution.
Actually, I probably didn't follow this slide. I don't know the difference between this one and the early one that you do a classical projection measurement to a probability P. What's the difference for this setup in this slide?
Here, I'm basically trying to put forward language that encapsulate the previous situation. You know, I'm saying that, you know, this measurement plus random circuit, well, sorry, random unitaries interspersed with a measurement falls under the category of random ensemble of non-unitary circuits. But this idea is rather general. If you were to start from this more general idea and try to come up with, you know, with these extra conditions, it's effectively a physical system with its non-unitary solely realized by measurements. But we could have other source of non-unitarity due to coupling to a bath or other sources, some decay loss in your system. In those cases, the non-unitarity will not come from measurement, but it may still fall under the category of random circuit ensembles, not a random ensemble of non-unitary circuits. Does that answer your question? And yeah, so and then there are some smaller details that you can tweak that may or may not change the criticality. So this is sort of a microscopic requirement if the non-unitary is only coming from measurement and nothing else. How much of it matters? It's a thing that is being investigated right now.
What's this condition? This POVM condition. This is the condition imposed on every site.
No, it's just that if you view the entire circuit as C, you know, for every realization of, you know, green boxes, every possible measurement outcome here and there, all possible realization, it gives you a collection of C. The C means the whole circuit. So
but you have a summation of C dagger C. So what's the summation there?
The summation would be, say, here it's going to be integration over the random ensemble for each of the green stuff, summation over all possible measurement outcome, and maybe summation over all possible distribution of where the measurement is. This is what the summation means. Meaning that you sum over all possible circuits in this ensemble.
Okay. And sorry, then the non-unitarity comes in which, how do I see this? Just where's the
I mean, C does not have to be a unitary operator in general.
Okay.
For example, if C
for each circuit, for a given circuit, it does not need to be unitary.
Yes, for a specific C, it's not unitary. For example, for specific realization of C, I have unitaries combined with projectors in these red sites.
And you say the slide you show, that one does not require measurement induced. It doesn't. The criticality is not due to measurement induced. It's not induced by measurement. Can you clarify that again? Yeah.
So yes, in the earlier setup, certainly measurement is the only ingredient because we, you know, or I would say that the non-unitarity is coming from measurement. But right now, it's still debatable. But I think, you know, at the very least, it's induced by non-unitarity. For sure, but you know, whether or not that non-unitarity has to come from measurement, it's something to be studied. But
okay,
at the very least, you know, it's induced by some form of non-unitarity. For example, in this case, certainly, having non-unitarity in this setup, makes it possible to have a entanglement transition, even though the circuit reinterpret out of this tensor network study does not have to follow this POVM conditions. It's certainly not coming from measurements.
Thank you very much. May I phrase in maybe a general way, is that the earlier part that you have a measurement induced, that it impose local condition for measurement on the local site of the circuits and projects the quantum state to with certain probability p to some specific state. That's a local constraint, and then that local constraint is imposed by measurement. While here, especially the POVM is a global constraint on some ensemble of circuits. Is that a way to think about this? So
I would refrain from using local and versus global. Yes, indeed, this is sort of a more global setup, but but in a real system, I don't want like full non-locality. So my circuit is still built out of local stuff.
Yes, it's a local circuit, but there's some global constraint, maybe more like a constraint on choosing an ensemble or something like that.
Correct. Yeah. So long as you follow this constraint, it can be interpreted as a circuit that with its non-unitarity coming from measurements. Okay, you don't have to be going into the microscopic detail to ask which part is measurement, which is not, to discern if your physical system is have the non-unitarity induced by measurement. Yeah.
Okay, thanks. Is there some kind of gauge degree of freedom or gauge constraint for the POVM? I don't know, just random asking.
Gauge, I'm not entirely sure of what that.
I also don't know. I know. Okay, thanks. Is enough. Thank you.
Yeah. Could I quickly ask, could you clarify the role of time here? So you've indicated that late time, but are you actually observing the time evolution in terms of the observables that may be interesting there? Because I haven't detected any sort of universal observables that are time dependent.
Right. Yeah. Oh, okay. When I say time, it's really just this vertical direction, the circuit time. So presumably I'm thinking about a circuit that has a growing length. I'm not going to just stay with a fixed set of circuit ensemble, but rather I have a time direction. I'm interested in what's happening when the circuit becomes really, really long.
But is there any power law in time that you're looking to detect in this process?
You could go into the bulk of the circuit and try to measure some time dependence in it, or try to keep track of how the initial product state, the initial growth of the product state in terms of entropy and other stuff. That one can certainly do. Okay, thank you. Right, but I guess I introduced the final state entanglement entropy. Really, this is a probe of something happening, but we are not bound to only analyzing the final time slots or the saturated value of the entanglement entropy.
Yeah, it was just the extent to which that type of structure of time dependence was interesting.
Yeah, in fact, in this paper, we map it to a StatMag model. So this would be the bulk of the StatMag model. So you could certainly measure bulk correlation functions and try to translate it back to the circuit language and ask what those means. And certainly, there is some interesting quantity to be explored.
Yeah, super, thanks.
Yeah. Okay, so
Chao-Ming,
yes.
Is it possible to realize the entanglement transition without randomness?
Right. So I guess this is a good question. As in, if the standard is I guess there's this recent work, that talks about what could happen with a single how should I say, a single non-unitary Hamiltonian. So I guess you may or may not want to call that an entanglement transition, as in maybe those states may have some dependence on the initial state that I'm not completely sure of. But this type of setup doesn't really care about those details. So I guess this notion of entanglement transition at this point is still flexible, as in maybe you could put in your definition and see if your system give you some transition at the level of entanglement.
I see.
Maybe rather just keep it general at this level, yeah. And also in this setup, really, there's no other structure than entanglement to explore, if I may say. There's no symmetry, no other details, and there's not a fixed Hamiltonian. So I guess this sort of setup single out entanglement as the most important quantity. But once we have more structure, like for example, a specific Hamiltonian, maybe with fixed non-unitary terms in it, then whether or not it's something that completely triggered by entanglement or is just some entanglement behavior piggybacking on other forms of criticality, it's something to become, well, it would be something that is debatable. Yeah. Okay, so yeah, so now this is sort of a general view that I'm going to take, but all these are interesting, but generally analyzing a random ensemble of non-unitary circuit is not easy, and not even the form proposed by these two earlier works, the criticality there is not completely understood in the sense of the full universality class and all the critical exponents and all that. We certainly have already collected a lot of numerical results on that, but just full analytic understanding is still to be developed. So far, I think we have found an exactly solvable limit coming out of deforming the earlier setup. But if I were to be honest to the previous setup, then I think there are still things to be done in understanding that the universality class, and even in those are the most the models that it was introduced earliest. All right. So certainly, to gain more intuition, it's certainly helpful to try to come up with models, of entanglement criticality, where you can analyze things more systematically and more analytically, and try to extract from them what are the general structures. All right. So this is the thing that I want to focus on mostly, maybe with the remaining half an hour of the talk. That it's this work that we put out last December, which is about entanglement criticality in non-interacting fermions. I guess when something is hard to solve, and I hope you would agree with me that if you think about the random, the circuits, the dynamical system on a circuit of qubits, you would call that an interacting circuit in the sense that all the spins or qubits are interacting with each other in a dynamical setup, right? So I guess the first instinct of finding something solvable, more solvable at the very least, is to go for non-interacting fermions. And indeed, that's what we try to do. And then hopefully trying to gain more intuition. And it's actually quite interesting that even this seemingly simple setup of non-interacting fermions gave a lot of structures. And also there's other perspective, as in simulating a random circuit plus measurement. If the random circuit are random unitaries, hard random unitaries, or just random unitary group drawn from a random unitary group, it's going to be very hard to simulate, because you have to basically diagonalize the whole circuit to understand its late time behavior. So that's really costly in numerical simulation, right? So, but for non-interacting fermions, we are almost certain that we can always do very large size calculations and see what's going on, at the very least at the level of numerics, right? Okay, so yeah, so that's certainly something motivating us to study non-interacting fermions. And let me define this terminology: non-unitary Gaussian circuit, NGC. I guess non-unitarity just means non-unitarity. I'm just going to explain what Gaussian means. So this is a circuit acting on a 1D chain of fermions, a chain of Majorana fermions. Possibly I have multiple Majorana modes on each site. And then when this is a Gaussian circuit, it means that every single gate is taking this form, exponentiated. It's an exponentiated bilinear form of Majorana fermions. That's what these gammas are, with coefficients m, not necessarily forming there's no constraint on m. If you require these gates to be unitary, then m has to form has to form a matrix that is identical to basically it's an I times a Hermitian matrix, right? So with that condition, the circuit would be unitary. But since we're focusing on non-unitary circuits, I have no constraint on I for the moment. the very least, right? But we certainly encounter evolution of this kind before, even when we study just the imaginary time evolution of a Hamiltonian system. Something like that would come up. So this is not something that is not reasonable. And then here I'm going to consider random ensemble, meaning that every single one of these gates are first of all independent and may have some random coefficient m. And we want to try to keep track of what's happening for this type of circuit. Hopefully try to find interesting structures. And indeed, yes.
What does I and J, what do they run over? The indices I and J?
I and J, so each gate acts on two sites, but I possibly may have multiple Majoranas per site. So it's going to run over the Majorana index on the site that is being acted on.
So is that something you can choose, or is that?
Yes, you could. I mean, for example, if I talk about, say, a complex fermion chain, but I don't care about U1 conservation, that effectively I have two Majoranas per site, two Majorana operator per site. You could change that. And I will actually explain some phenomenon that is associated with changing that when it comes to criticality at a later point.
Thanks.
Okay. Yeah, but so far I'm just basically setting up the problem and motivating why we study this. And I mentioned this before, as in large scale simulation would be possible in this type of setup. And then actually, this is not just purely going for solvability, but in fact, there is some interesting thing that may be more specific to non-interacting fermions or Gaussian circuits. As in, there are evidence saying that entanglements store in states of non-interacting fermions. For those, you may want to just think about Slater determinant states, for example, if you have U1 conservation. Entanglements stored in those states are more vulnerable to non-unitary operations, for example, measurements, and maybe other form of non-unitaries. There are even arguments or evidence or analysis against the existence of a volume law phase in such a type of systems. Right? So especially this later work focused on 0+1D circuits, 0+1D circuits acting on a quantum dot. So I would only have a time direction, no space direction. And then there's even a proof that the volume law phase is not going to appear. Right. Okay, so this is something more specific. And then maybe actually a difference between non-interacting fermions and cases with interactions, like the earlier setup that I introduced. Okay, so this is sort of the general setup.
Excuse me, sorry.
Yes, go ahead.
You say arguments against volume law for specifically for what? For non-interacting fermion?
Yeah, basically for this type of non-unitary Gaussian circuits ensembles.
Okay, with those gamma matrices. And
those, sure, yeah.
So what's the key constraint here? Against fermions or against?
No, not against fermions. Against entanglement. So you basically, well, the statement is that you won't be able to see a volume law in a phase, in a state consists of non-interacting fermions. For example, you won't be able to have a volume law in a Slater determinant state. If there's not,
how about interacting fermions?
Well, yeah, there's no argument against those. And then basically you could always reinterpret the earlier result as some interacting fermion system as well. So for sure, volume law phase exists there. So it's nothing against fermion. It's something more particular to non-interacting systems.
But can I bosonize, fermionize the system and then view this as some bosonic system, but then there's no argument against volume law for the bosonic system?
No, I would say that in those cases, there will be specific arguments against those particular bosonic system that is dual to a free fermion system. It's not like every single bosonic system can be dualized to a non-interacting fermion system, right?
So what's the dimensionality in your calculation? It's a 1D or it's a 2D system?
So the circuit lives in 1 + 1 space-time, for example. Well, I mean, I'm gonna generalize that, but this circuit that I'm drawing has vertical direction as time, horizontal direction as space, the chain.
So basically it's just a quantum chain in a simulation.
For this one, yeah, but I'm gonna comment on higher dimension as well. Yes.
Okay.
Yeah. Okay, so this is the setup. And then before going into the technical part of analyzing if there's a criticality, there's a nice language that we can make use of, which is actually setting up sort of a correspondence between non-unitary Gaussian circuit and the so-called Gaussian tensor network. All right. This correspondence, I think it's rather simple or almost tautological, as in if you think of circuits as just a bunch of unitaries or non-unitary gates multiplying together or contracted to each other following certain index contraction rule, you could always just think of it as a tensor network, right? So, but there is a slight shift of terminology, as in I always make the vertical direction as time for the circuit, but for general Gaussian tensor network, there is no no necessary distinction between. I don't necessarily have to call the upward direction time, the horizontal direction space, but you could always just follow the standard operator to state mapping to convert every single node into a state, and then by this contraction, I have a tensor network. Right? But it's slightly different from the tensor network that we are used to dealing with in condensed matter setup, as in there's no bulk leg that is uncontracted. Everything is contracted in here. Right. This is a change of language, but it's a rather convenient one because I could do this node by node. So every single Gaussian gate can be converted into sort of a 4-leg tensor that is represented by a pure Gaussian state. All right. So what is a Gaussian state? If you like to think about complex fermions with charge conservation, then Gaussian state really is just a synonym for Slater determinant state. But here I'm dealing with Majorana fermions. So these are general state that is completely defined by 2-point functions. Higher point functions are just coming out of weak theorems. That's what I mean by Gaussian state. Okay, and then the reason that I introduced this is that it's much easier to formulate the randomness in such a setup for the Gaussian states. For example, there's a naturally defined maximally random Gaussian states, in the tensor network language. That would give us some sense the maximally random non-unitary Gaussian circuits. The reason why I don't define things straight up here is that there's no non-unitary gates are living in a non-compact space. If you think about all possible parameters, so there's no natural hard measure to speak of in here for the circuits. But if you translate it into tensor network, you could formulate the randomness much more convenient. All right, here I won't give you the exact parameterization and a lot of details for reasons that will be clear in 2 slides, hopefully. And then I'm making almost everything random, completely random, especially in this side, the tensor network side. So there's certainly no symmetry whatsoever, except for fermion parity that I'm going to have for the random Gaussian circuit. So that's the very first thing that I'm interested in. I can simulate the circuit, or in the same language, I can, just a shift of language, I could simulate this tensor network using whatever technique that is to our advantage. And either it's rather simple to simulate and can go into rather big system sizes, right? And this is sort of a technical thing that, but I would like to just briefly mention in passing. It's not hugely important, but I just want to be faithful to what I said, what we study. As in, you could read the tensor network upwards and think of it as a circuit, or you could just think of the 45-degree direction as the time. It's a new time, maybe, that is different from the circuit time, but it doesn't really matter which way you think of as time, for the final outcome. But as it turns out that we turn the circuit or tensor network 45 degrees and simulate it as if the V direction is time, and look at what's happening at large V. Okay, this is just literally what we did, and then we also impose periodic boundary conditions in this direction. So
I would have some initial state for v equal to 0, represented by the blue dot. I'm going to keep track of what's happening on the final time slice. These are the numerical simulation, which I hope to show you. The reason why I don't tell you specifically what kind of random ensemble it is that we are using is that as long as we're close to, somewhat close, I mean, in a rather large parameter regime, including the maximally random case, we observe a critical phase, right? So this is very different from the previous situation where we have to fine tune the parameter P to hit the critical point. In this non-unitary circuit of Gaussian, this non-unitary Gaussian circuit, NGC, we actually see a non-fine-tuned criticality, meaning a critical phase. So there's no real need to tell you specifically what kind of ensemble they were using because we're just going to hit a phase, right? So slight change of parameter is not going to go, bring us out of the phase. This is what we look at. We look at the so-called final time slice or just long time limit in terms of this time given by V, and look at half system entanglement entropy. Look at how it scales with the system size. It always follows a log behavior. This is what these lines are. But you see multiple lines indicating different prefactors. And then these different prefactors are for different systems with different number of Majorana modes per site. So this is, this is a plot of the prefactor as a function of number of Majorana modes per site. So you see a very interesting linear behavior. The more Majorana modes you have per site, the bigger you have, the bigger prefactor in front of the log, right? So I said this is a criticality because for one reason that this resembles what we see in the entanglement critical point in the earlier setup. And also you could try to look into the finer detail of this model. For example, you can look at not just the entanglement property, but you can look at the behavior of the correlation functions at the final time slice. If you simply just average over all correlation functions, then you're just going to get 0. 2-point functions, literally take that average, you're going to get 0. But if you square it and average, you get something rather non-trivial given by this plot. And it fits very nicely with this behavior, right? So R is the separation of the 2 points. I have 2 points, 2-point functions measured at the final, the long time limit, and then I square it and then do the averaging over all circuit realizations. I have this funny formula, this funny looking formula where I have a power law. This is actually related to the criticality, and 2 is a certain scaling exponent. The reason that there's a log included in here will be clear a few slides later. But I think if you forget about this 1 plus log term, then A over R squared is a sign of criticality. Again, another sign of criticality. But adding this term to the problem makes the fit even better, right? And then it's actually informed. It's informed by the theory. In fact, it's not just some random choice of fitting functions.
Question?
Yeah.
Is there a corresponding result for unitary free fermions?
Unitary free fermions most likely. Well, actually, we simulate that. Yeah, we're just going to get volume at the final time slides.
So you will not have this criticality. Is that?
Yeah, so this is a critical phase. If we end up just having no non-unitarity whatsoever in the system, then yeah, like the entanglement entropy is going to scale with L. But that's a fine-tuned limit in the sense that if you add in any non-unitarity, things would change probably.
No, but about the square 2-point functions, is there a?
Oh, you are asking what happened there. I think most likely you're just going to get a, oops. Oh.
Sorry.
My PowerPoint crashed. So.
Yeah, I asked a bad question, sorry.
Sorry, let me put the slides up again. Okay, I think it's coming back up. Right? Yeah, so oops. Right, if you perturb the unitary circuit by non-unitary, things would change very quickly. So, but there won't, the expectation is that there still won't be a volume law phase, so long as you don't have unitarity. Does that answer your question? Oh, you're saying what's the 2-point function? Sorry. Yeah. Yes, I think I would expect just exponential decay in that case.
Okay. Thanks.
Yeah. Could I come back quickly to the question about time dependence? So here at the late time, at what times are you sampling to get this scaling log law?
What time?
Yeah,
well, it depends on the system size. It will depend.
So how does your sample time, what you call late time, scale with L?
Well, yeah, it will. So yeah, like the larger size.
I'm asking what is your observed empirical observation of the right time to make
the right
your observation?
I think I have to at the very least go as the same size at the very least. Just think of the circuit as being sitting in a sort of a square box, or with certain fixed aspect ratio at the very least. Does that answer your question?
No, I was just trying to quantify again what you meant by long time, because you're simulating.
Yeah, so long time as in. Yeah, so basically you're asking about basically the aspect ratio of the whole entire circuit in the space-time picture. Right? Mm-hmm. And yeah, it has to be order 1 at the very least.
Okay.
Yeah. Or sometimes you have to go slightly longer, but okay. We haven't done very systematic analysis and asked.
Back to the equation of the exponent, I guess that's what I was touching on. If there's
we haven't got those yet. We are mostly analyzing the final time slides.
Sure, thank you.
Yeah, but and also different quantities seem to saturate at slightly different time as well. So that is also maybe.
Yeah, that was kind of what I was trying to understand, is whether there's a prediction about what the scaling laws should be for when those observations should be made, or vice versa.
Right. Yeah, but for final time slides, all I'm trying to see is some saturation, and I start to look at what the behavior.
Understood. Thank you.
Yeah. Okay. So. So the idea so that was just numerical observation, and then I said that this form is actually informed by a theory understanding. Let me just sort of get to that. What is the theory understanding, and what kind of picture is behind this? So ultimately, we're dealing with some non-unitary evolution of, basically free fermion, and then since this is a non-interacting system, so things can be solved at a single particle level, right? If you keep track of how a single fermion operator evolved, this already tells us what the circuit is, because we have no interaction. The non-unitarity is not going to, create a problem for this, because we actually have already dealt with a non-unitary evolution, even when we try to think about, the evolution of fermions with a Hamiltonian system in complex time, right? In those cases, it's not a sort of a unitary evolution. But nevertheless, we will be able to keep track of the propagation of the fermion operator in the circuit. Right? The propagation of the circuit is going to will be produced by the single particle version, the first quantized version of the circuit. Right? Even though I formulated it in the second quantized form, and there's a single particle version of it that tells us the fermion operator at a single time slice at T1. How are those related to the fermion operators in a different time slice, a later time slice, for example? Right. This is basically a linear relation between fermion modes in the circuit, and this is generated by the linear relation introduced by each one of the gates, or each one of the nodes in the tensor network. Right. For each node, I would have. Well, for simplicity, I only write 4 fermion modes, but there could also be indices. Multiple modes living on one legs, but nevertheless, I hope you just I hope you just get the picture that there's some linear relation induced by what's in here between all these four fermion modes, or fermion modes living on the 4 legs. Right? There's some linear relation. Obviously, these linear relation will be different if you choose a different gate, a different tensor at a single node. But this is somewhat reminiscent, or this at the very least reminds us of a quantum mechanical scattering problem induced by Hamiltonian, meaning that I could have a scattering center here inducing, and then think about a static situation, no time dependence, and I would have some linear relation between the incoming modes and outgoing modes, right? But at this level, it's rather a superficial comparison, as in I'm just comparing linear relation in the circuit setup with linear relation that one can get from a quantum mechanical scattering problem. For the latter object, quantum mechanical scattering problem with a Hamiltonian, we certainly have to decide what are the in-state and what are the out-state. And with proper definition of them, one has to check that the scattering S matrix is unitary. Otherwise, this comparison would be just completely superficial. And indeed, if you just have this circuit and you try to come up with an understanding for a quantum mechanical scattering problem, you would not succeed because there won't be a unitary S matrix associated with that. However, in fact, it's rather natural to think of the circuit and its conjugate at the same time, right? This would be evolving a single state, but this circuit and its conjugate tensor product together, not multiplying together, tensor product together, are really something that one would make use of when we think about the evolution of the density matrix. This controls the evolution of the ket state, and this would control the evolution of the Bras state. But if you think of, if you overlay these two circuits on top of each other, before we do any averaging, we could actually make use of an analogy that I mentioned just now. As in here, you could actually map it to a square lattice network of scattering problem with each node representing a unitary scatterer, meaning that there's a well-defined set of in-state and out-state, and there's a well-defined S matrix that is unitary. So supposedly, with that, I could reinterpret that as coming out of a Hermitian Hamiltonian. And this mapping is done realization by realization. No disorder average is needed. One also interesting aspect is that for the circuit, I would say the vertical direction is time, horizontal direction is space. But for this network, I would just interpret all the direction as space because I'm thinking about a static scattering problem or elastic scattering problem. There's no time dependence in here. All right. Okay, so this is an exact mapping, and this is what I said already. If you map from here to here, you get a network of scatterers with unitary S matrix. So we could think of this as generated by a Hamiltonian, a Hermitian Hamiltonian, very important. If you look at the details, it's not only just an exact mapping to a network of unitary scatterers. These scatterers also have a particular set of symmetries, right? So in fact, there are three different symmetries that I want to talk about: chiral symmetry, time reversal, and particle hole. Let's talk about chiral symmetry first. So here I'm saying that I have some network circuit and its conjugate overlaying on top of each other. So two pieces of the network. Fermion modes propagating on this side is not going to jump to the layer, this layer, and vice versa. No fermion operator propagating in here will all of a sudden jump to this layer. And this is, in fact, an effect of this chiral symmetry, separating the two layers. And also, there are symmetries that exchange these two layers. There are these time reversal and particle hole symmetries. And the two are related to each other by by a multiplication of the chiral symmetry action. So we're not only just dealing with a network of scatterers, but we are also dealing with a network of scatterers with chiral, time reversal symmetry, and particle symmetry. And bear in mind that I have imposed no symmetry for the circuit, and these symmetry just automatically emerge realization by realization in the network of scatterers that we map to. And in fact, for those who are familiar with Chalker-Coddington models, you would immediately realize that this is actually, I'm talking about a Chalker-Coddington network model. And with these symmetries, and also with this specific rules, t squares to -1, particle symmetry squares to +1, exactly given by this mapping, we're sitting in the so-called symmetry class D3, or one of the 10-fold symmetry classes or disorder system.
I mean,
yes.
So is there a one-to-one mapping between your Gaussian circuit and the topological superconductor or topological insulator?
That's a very good question. So in fact, there are some subtleties in describing those topological state using Chao-Ming network, as in one has to carefully keep track of what's happening on the edge and impose proper boundary conditions. So right now, we're still thinking of that. If if I can pinpoint which one circuit is corresponding to the topological state, which one is not. But the boundary condition is some subtleties that we have to resolve before we can answer that question.
Well, but so 10-foot away is for unitary.
Correct. Yes.
Right. So
this side is completely unitary. There's no non-unitarity for the scatterers.
I see.
So yeah, so it's somewhat amazing that something that has no symmetry and non-unitarity got mapped to
I see
a network of scatterers with symmetry is coming out of almost nowhere. Well, I shouldn't say that, but it's coming out of the setup, and it's done realization by realization, and unitarity, you could say, emerge coming out of this mapping. But this is a model without time. Okay. In the interest of time, I was hoping to give you a very quick lightning overview of Chao-Ming model. Let me just try to keep it brief, but just mention where it comes from for those of you that are not familiar with. So it was initially introduced not for the symmetry class D3, obviously, it was for class A, and the original target was the quantum Hall Plateau transition. So if you have disorder and non-interacting fermions in magnetic field, you would have different puddles with different lambda level occupancy. For example, you may have 0 lambda level occupancy, you may have 1 here, and there will be chiral edge modes, right, in the interface. And then the Chao-Ming network is really trying to represent the network of these chiral modes. Obviously, it's going to be disordered in the real system, like this shape of the network, but as it turns out, it does not hurt if you just put it on a regular grid. And then it's not a static network, but it's a network, but these chiral modes are not completely independent from each other. There will be scattering happening across this network. If they get close enough, these are kind of formally represented by these nodes, introducing the scattering between the chiral modes. Right? And the merit of doing non-interacting fermions makes us possible to focus on a certain frequency. And oftentimes, the important physics only happens on a fixed frequency in many cases. So that helps us to go from a 2+1 dimensional problem, a unitary problem with a Hamiltonian, a non-interacting disorder fermion. We can just Fourier transform from it into the frequency space and focus on the specific frequency where interesting physics happen. That way, we end up having a model that is only living in the 2-dimensional spatial slides without an explicit time. But nevertheless, this is describing a 2+1 dimensional Hamiltonian system of disorder fermion without interaction. And all the physics is hidden in the S matrix, how specifically these modes are scattered at each node. Just to give you a picture, for example, if you choose some scattering so that the network goes like this, and sometimes you see a chiral edge mode running in one direction, one edge, at the overall edge of the sample. Sometimes you just don't have that chiral mode. Obviously, this will depend on the boundary condition, but this is sort of telling you that by thinking of the physics coming from the S matrix, you could realize different phases. And these are the easier one to describe. You can have disorder fermion phases that are of more complicated form that is not simply represented by these simple pictures. But basically, I'm trying to say that Chao-Ming network model is just a faithful representation. It's another representation of non-interacting fermions with disorder. Yeah. Okay. The initial model was introduced in class A, but you could go for any of the 10-fold symmetry classes in the Outland-Zimbauer symmetry classification. All right. So basically, what I'm trying to say is that with the mapping from the circuit to the unitary scatterer, we are basically mapping the problem of non-unitary circuit, entanglement type problem in the non-unitary circuit, to the problem of unitary models of disorder fermions. And in particular, the entanglement criticality seen on this side, at the level of numerics at the very least in the beginning, is actually mapped to a unitary disorder metallic phase. on the chocolate cognitive network model, and it's sitting in class D3 in 2 spatial dimensions. So really the unitary disorder fermion system is sitting in 2+1 dimensional, if you will. And the entanglement criticality can be mapped to that disorder, disorder metal. And this specific form of the 2-point function is really informed by the theory of this disorder metal. In particular, the 1 over R square is some, it's some exponent. Well, this metal is actually described by a conformal field theory. It's essentially a free boson, but one has to take the replica limit. So it's actually limited with zero numbers of zero numbers of boson, free bosons. So I have a 1 over R square, giving us some conformal scaling form, and then this log R is actually some well-known marginal irrelevant perturbation that actually plays an important role in such a disorder metal. With the conformal symmetry, you can relatively easily understand why there's a log entanglement entropy, which I don't have time to go to. And then this metallic phase is stable. It's a stable phase. Hence, that's why we're seeing a stable entanglement phase in the circuit side. If you really want to transition out of this metallic phase, you have to introduce sufficiently strong staggering in the model, meaning that you want to distinguish the A sublattice and B sublattice in this network and make the scattering very different between the A sublattice and B sublattice. Only with sufficiently strong staggering, you could get out of the metallic phase or the entanglement critical phase and end up having a volume law phase. An area law phase. Still, there's no volume law phase here. It's either critical phase with a log entanglement and the area law phase. Okay, so actually, this analysis actually is underlined by a rather general picture, schematically represented in here. It's a correspondence between, it's rather big correspondence between 3 objects, non-unitary circuits acting on d-dimensional fermions. That's where we start with. I don't have to talk about circuits acting on a single chain. Could be any dimensional. And due to this operator state mapping, I can always convert it to a Gaussian tensor network, right? And then the space, this is acting on d-dimensional fermions. So in terms of space-time, I have a d-dimensional space-time in here. Hence, the Gaussian tensor network will be living in d+1 space-time dimension. This correspondence is rather simple, but mostly what we have shown in the paper and this talk is that both of these are also dual to a chocolate cognitive network that describes unitary system of disorder fermion without interaction in d+1 spatial dimensions. Hence, you could convert any knowledge in here into this setup or into this setup. And we have done so for the class D3. No symmetry in here correspond to symmetry class D3 in here. And we have shown that the disorder metallic phase in here should be identified with the entanglement critical phase in here. If you're interested in any other 9 symmetry classes for the disorder fermions, unitary disorder fermions, we provided a recipe in the paper, what kind of circuit it corresponds to. Okay, so I won't be able to go into the details, but a rather simple one can be explained here. If you just want non-unitary circuits with U1 conservation, okay, so instead of Majorana fermions, I could switch to complex fermions. Then the disorder fermion problem it corresponds to from the chocolate cognitive network perspective is sitting in class A3, for example. Okay, so this is a rather simple constraint you can have. And entanglement critical phase is still a critical phase that I will have for 1D chain will correspond to a line of fixed points in class D3 into class A3 in 2 spatial dimensions. Right. Okay, I promise that I will comment on higher dimension. So one thing in particular one can say is that in higher dimension, disorder fermions, unitary models of disorder fermions would always exhibit a disorder metal phase. It always exists. That means entanglement criticality is rather generic in higher dimension. And what would be the form of entanglement criticality when it comes to entanglement entropy? It will be taking this form. There's not only a log, but actually there's an area law piece. if we go back to the one-dimensional, 1 plus 1 dimensional circuit, this volume law piece is going to give us a number. So I restore this law of behavior, but generically one should expect that. And we have some numerical study evidence showing this behavior as well. So this is really what we should expect for entanglement criticalities in higher dimension. Okay, I think with that, I will put out the outlook slides, as in, this, I believe, generates a lot of interest. I've been dealing with the non-interacting fermions, non-unitary Gaussian circuits, but certainly it would be interesting to include interaction and see what kind of phenomenon would change. For example, to see if the volume law phase will immediately emerge, or it still takes some amount of interaction to make sure that happens. And the other point would be that, so as Senko commented, that the incorporation of topology would be an interesting direction to see what kind of circuit exactly correspond to the topological phase and which circuits are corresponding to the trivial phase. And also in the paper that we discussed, mostly we were discussing tensor network that correspond to NGCs, to circuits. And in fact, those are tensor network that come out of pure states. But we also show that even mixed state tensor network can be mapped to Chocker-Collington models. So maybe there will be also some interesting form of entanglement criticality there. And in the end, I would also like to comment on that, the statement that there might be a no-go theorem yet to be proven in generality, but there might be a no-go to volume law phases for non-interacting fermions. And it would be nice if one can make a complete proof of it. But so far, I guess it's fair to say that it's unlikely a volume law phase would appear based on all of the studies in this work and also in previous or other work. All right, I think with that, I will thank you for your attention. And I'm happy to take questions.
All right, so about the last point about the volume law phase is a non-unitary Gaussian circuit. So, so that will depend on what the initial state is, right?
Yes, so here I'm always starting from a, yes and no, in the sense that for convenience, I would like to start with a somewhat like a product state or some low entanglement state. But remember, there's non-unitarity in the circuit. So if you really start with a mixed state, it actually gradually gets purified. This is actually a perspective provided by Gollins and Hughes. Let me just take a step back, or sort of take a zoom out view and just think about non-unitary circuits, not necessarily for non-interacting fermions. For example, if I'm back to this setup, start with a mixed state. Each of these projectors is going to decrease the entanglement entropy. And with sufficiently many of such projectors, combining with free fermions, this paper by Fidovsky, Haar, and Hastings shows that at least for the 0 plus 1 dimensional system, it eventually purifies. The final state becomes a pure state.
Yeah, right. So it looks like the real theorem should be that the entanglement entropy does not increase during the non-unitary Gaussian circuit, right?
Oh, it certainly will increase, because if I start off with a product state, or almost product state, then
yeah, right,
it will grow. So yeah.
Okay.
But it's to what extent it can grow. It's
yeah.
Okay.
More questions, comments, suggestions?
Can I ask a question? This is about, like you mentioned in your introduction, I guess, that there's a non-unitary CFT that you observe. Is that this critical point that you talked about at the end, or is that something else? Oh,
yeah. Thank you for the question. Yeah, so for the non-unitary circuit plus measurement, in the solvable limit, we could identify that the universality class as just a percolation universality class. But for these NGC, this non-unitary circuit for non-interacting fermions, it's a different set of a universality class we're talking about. These are the theories these are the conformal field theories that describe these disordered metals. Where is it? I didn't mention it, but if you go for a replica type treatment for these disordered fermions, these disordered metallic phase end up being just free bosons in two dimensions. But there's a trick to it, as in, or you could say nonlinear sigma model. It's at critical point. But bear in mind that these all has to be done at the replica limit. That makes things kind of non-trivial and non-unitary.
I see. And can you figure out what the other side of the correspondence would look like, where you have non-unitary Gaussian circuits?
What is the other side? Sorry, could you?
As in, like, yeah, you find the. I mean, you're talking about the criticality for the Chocolate-Coddington side of this correspondence. What can you say about the left-hand side of this?
Oh, because there's an exact mapping from one side to the other. So I would say that basically the theory of the disordered metal is the theory of entanglement criticality.
I see. Okay, but your right-hand side is unitary, but your left-hand side, like one copy of the left-hand side is non-unitary, right? So
yeah, but that doesn't matter. As in such a I don't think that's something to be worried about.
Okay, thanks.
So I'm curious about the higher dimensional case. Let's say two spatial dimension.
Yeah.
We know that a unitary CFT in 2+1D, its entanglement entropy follows the area law, right? There's no log.
That being the ground state.
Yeah.
That being the ground
state. But now the entanglement criticality will have rather different entanglement scaling behavior.
Correct.
It's different from like one spatial dimension.
Yeah. So I guess even though they are both entanglement entropy, but they're not really the same object if you go into the guts of it, the theory part of it. As in the entanglement entropy in the circuit setup is more like some boundary correlator type entity. So I would say that it's not such an entanglement entropy is not directly comparable to what you may have for a ground state of a CFT.
I see. So the one spatial dimensional case is just a coincidence.
I would say it's a coincidence. Yeah. Well, I think one thing that I hope maybe one can appreciate is that this certainly is the most natural form one may want to have. If you think of entanglement criticality between something between the area law and the volume law phase, right? If I only have a log and beyond one dimension, then log would be even smaller than area law. And that's kind of unlikely, right?
Yeah.
So this is more naturally expected for entanglement criticality in higher dimension. This is sitting in between area law and volume law.
I see. Thanks.
Yeah.
Could I ask a question somewhat orthogonal to what you had talked about, the introduction of interaction? So are there interacting systems that you've looked at where you've found, in some sense, an interesting tension between entropic effects and free energy?
Sorry, I'm not completely following. So you're asking about interacting systems now?
Well, yes. So if you have this dynamics, but you introduce an interaction term. So I'm interested in the thermodynamics of those systems.
Oh, I see. I guess maybe we should first try to come up with a set of definition what thermodynamics means, right? So
sure.
That already would be tricky, but I guess if you think about if you don't distinguish so much entanglement entropy with thermal entropy, then that may be one of the thermodynamical quantity that you want to look at, and certainly there will be others. So
no, just throwing the idea out there, just this notion that in some sense this entanglement entropy coupled and introduced into a sort of a more traditional thermodynamic perspective could be very interesting.
Yeah, I totally agree. I think I guess entanglement entropy is one thing that, first of all, it's universally applicable. I don't need the details of the Hamiltonian to define that notion, so that's why it's good. But that does not necessarily mean that that's the only thing I can look at in this type of setup. Yeah.
Super, thanks.
Yeah.
Any more questions, comments? In any case, let us thank Chao-Ming for the wonderful seminar. Thank you very much. 多谢大家. Thank you.
Thank you.